Yeah, good evening. Uh, I would like to demonstrate another example of using calculator block in this session. As you can see, we will not be able to handle this problem using conventional simulation without the aid of a calculator block. See, as per the flow sheet, methane and water are entering, mixed together and go to the reformer, wherein 99.5% conversion happens with respect to methane, and you are required to report the duty, the reactor duty, heat duty, because it is operating under isothermal conditions as a function of varying rate of methane, right? But one more issue here is, even though the flow rate of methane is changing from 100 to 500, for each of these flow rates, we need to maintain the flow rate of the ratio of methane to water at 1:4. For every 100 moles of methane that is entering, 400 moles of water should enter. In case if it is changed to 500, now the flow rate of water should be made 2000. And accordingly, using this particular mole ratio, we must be in a position to calculate the reformer duty. So let us try to handle this problem. So these are the components we are handling: methane, water, hydrogen, and CO. So let us define these components. For water, and hydrogen. So these are the components we are handling in the problem. Again, it's a simple problem. Only thing is, you need to know how to use a calculator block for doing some of the calculations which are not part of typical blocks involved with Aspen. So select from property model. Next, go to simulation environment. So as you can see, we are using a mixer wherein both the feeds are getting mixed and the combined feed is entering into a reactor. We were given the conversion stoichiometric reactor. Okay. So let us connect the input and output streams. For convenience, the other one is water. So let us go and try to define our problem. So as you can see, the temperature and pressure are not, yeah, they are given here. So you should be able to make use of these values. So we are going to use engineering unit system. So the methane is entering at 150 degrees Fahrenheit, 900 SIA, and the mole flow rate. Let me take the initial value of 100 LB moles per hour. 100 LB moles per hour. And this is entering at 70 degrees Fahrenheit and 15 PSI. 70 degrees Fahrenheit and 15 PSI. Corresponding to, of course, CH4 flow rate, which is taken as 100, we know that it should be 400, or even if you change it to some other value also, it doesn't matter. So many LB moles per hour. Next. Now let us see the conditions at which so we are also given the conditions at the exit of the mixer. So let us also define this. Specifically it is given, so it doesn't really matter as far as balance is concerned. However, when you are reporting the duty, affected by these conditions. So let me also go to the specify the pressure as 1100 degrees Fahrenheit, and the pressure drop pressure is given as 850. Having defined this, now let us we have taken care of this. Now the temperature at which the reactor is operating is 1450. So let us try to define this. So this is the reactor. The reactor is operating at 1450 degrees Fahrenheit of 20 psi. So minus 20 indicates any minus value defined for pressure will be taken as pressure drop. So this was taken care. Next. So we need to define the reaction. So CH4 coefficient is 1, water 1, and the products are CO 1, hydrogen 1. This stoichiometry is given here. And we were given that the conversion is 0.995 with respect to methane because water is in excess. Close. Next. Sorry, this should be 3H2, which I have not included. So let us go to specifications, reactions, edit. So hydrogen is 3. Now you can see the calculations are done, and we have not addressed the problem of reporting the duty, and we are not addressing the issue of varying the methane flow rate as well as maintaining the ratio of methane to water. First of all, let me introduce a calculator block, then we will try to use a sensitivity block. Say new. Okay. Now, what is that you would like to do? Whenever the flow rate of methane is changing from 100 to 500, so I would like to read the value of methane flow rate, right? So this is an input variable. It's a stream variable. Anyway, we are into pure methane and pure water. So mole flow. Stream is methane rate copper in LV moles per hour, right? So this is going to be imported, and based on this flow rate, I would like to calculate the water flow rate. Let's say WF. So this is an export variable. So it is also a stream variable. Mole flow. Stream is water, and component is again water. So what is that we would like to do? The ratio should be maintained in the ratio of 1:4. So go to the next. So the water flow rate should be made equal to 4 times the methane flow rate. So we are reading the value of methane flow rate and adjusting the water flow rate as 4 times the methane flow rate. Remember, we have specified the water flow rate, so that is going to be overwritten by the calculator block in such a way to maintain the ratio of methane to water flow rate as 1:4. Having done this, now let us also do the sensitivity analysis. Model analysis tools, expand this sensitivity. Now say new sensitivity loop 1, and what is that variable we are trying to vary? Say new. Varying the methane flow rate, it says mole flow in methane, component is methane. So we are trying to vary from 100 to 500. Let us say in steps of, you can take any convenient steps, though it is not mentioned. Let us say 50. What is that you would like to observe? We wanted to observe the duty, right? Say next, reactor duty. So this is reactor duty RD. Remember, it's a block variable. Block is reactor P2. variable is heat duty or duty calculated net heat duty. This is what we want. Remember, the reactor was operating at 1450, the input is at 1100. Moreover, depending on whether the reaction is endothermic or exothermic, as the reactor is operating under isothermal conditions, so heat is either added or removed. So that we are trying to report. Go to next, fill variables. We have now done both calculator block as well as sensitivity block. Okay. Right. Now let us run this problem. Now you can see the results. Of course, it is in BTU per hour. So the heat duty is now reported as you keep on increasing the flow rate of methane. The flow rate of water is also going to change, which is going to be 4 times this flow rate. If you want to observe what is the flow rate, you can also describe that in sensitivity. So let me define another variable, flow rate of water. Let's say WF. It's a stream variable, mole flow. Just to have an idea, mole flow, stream is water and it is H2. So again tabulate fill variables. So next. So you can now look at the results. Now you can see for every flow rate, automatically the calculator block is calculating the water flow rate as 4 times of the methane flow rate, 100, 400, 150, 600 like this. And accordingly, you will be able to see the value of heat duty. So you are adding heat, that means of course some heat is required to preheat the feed, which is coming at 1100 or 1150 to 1450, that is one. And in addition to that, we may have to add heat because it may be endothermic. So this is how you will be able to handle the calculations using a calculator block. Without doing this, is it possible for us to calculate, is it possible to change the water flow rate in accordance with the changes in methane flow rate without the use of a calculator block? So that's how you will be able to make use of a calculator block whenever it is needed. So with this, probably I'll try to close this session.